Okay, all right. So let us begin this today's session. This is week 12 and today we are going to do revision for all the sessions till week 12, week 11. So this is the last tutorial sessions and we are going to see the various concepts that are important for our final exam and so that everyone can get good marks there. So starting from the module 1, that is load characteristics and load management, and then we will go through the power distribution networks, a brief overview, and then we will see the module 3, reliability assessment of distribution network, and and just follow on we will see the load flow analysis of radial distribution networks, and then after we will see reactive power compensation of distribution system with shunt capacitors, how we improve the power factor, and what is the optimal placement and what is the optimal capacity of capacitors in distribution systems. And then follow on we will see the reconfiguration of power distribution network, and we will see these energy storage systems, and we have also saw several problems based on the wind energy, solar energy. So let us see starting from the module 1, that is load characteristics and load management. So the first question comes in our mind, what is load? What is electrical load definitions? Electrical load. What do you mean by electrical load? An electrical load, an electrical load is a device which consumes certain amount of power, certain amount of power, certain amount of power energy to accomplish a certain task. To accomplish certain task. So if we are saying that is the we are increasing or decreasing load, so always prefer to that this term power energy, that whether it is consuming more power or less power, so that we can say that we are increasing power, we are increasing load or decreasing load accordingly. So whenever we are saying that we are increasing load or decreasing load, always thinks in terms of power energy, that whether it is in consumption of power energy increased or decreased. If we are saying that electrical load has increased, so it means that consumption of power energy has increased. And if we are saying that electrical load is decreased, means consumption of power or energy has decreased. Based on the dependency of voltage, we can divide the loads into three different types. So based on the dependency of voltage, we are having constant power load, that is power is constant regardless of voltage. It does not depend on the voltage level. And second one is constant current load, in which power is proportional to voltage. And third one is constant impedance load, in which power is proportional to voltage squared. We know that power is equal to voltage into current into power factor. So we can write power is directly proportional to VI. If we are increasing voltage, it means current will reduce such that the power remains same. On the other hand, if voltage reduce, then current will be increased. And for the second type of load, constant current load, that means we know that power is directly proportional to voltage and current. It, this this is constant, so we can remove this part. So power is directly, sorry, I is constant, so power is directly proportional to voltage. And some of the important examples for constant current load are welding units, smelting and electroplating processes. And for constant impedance load, we can write power is directly proportional to Vi. After substituting I is equal to V divided by Z, power is directly proportional to V square divided by Z. Since we know that Z is constant, this term is constant, so we can remove this. Z is constant, therefore power is directly proportional to V square. It means that in this constant impedance load, power is proportional to voltage squared. And the examples are incandescent lighting, resistive water heaters, etc. Now, for this module, continuously we can see that about load factor. This is very important parameter for utilities, load factor. And it is defined as the load factor is the ratio of average demand to the peak demand. Load ratio is the ratio of average demand divided by peak demand. And always our utilities preferred this load factor should be preferably near to unity, because in that case average demand approximately equal to peak demand. In that case what happens is that whatever is the capacity of generation, that almost equally we can having utilized in that case. So for this utilities in that case our price will reduced, because whatever it is generating, most of the power demands, most of the power is being utilized. So that's why we can say that load factor plays key role in determining overall cost per unit generated. It plays a key role in defining this cost per unit generator. If load factor is lesser, that means overall cost will be increased. And if load factor is near to unity, then overall cost will be reduced. The higher the load factor of the power station, the lesser will be the cost per unit generator, as I said. Higher the load factor, the lesser will be the cost per unit generator, because whatever the capacity of generation that is almost utilized by the that most of the power demand is being utilized. A load factor means high maximum demand and low utilization rate. Means maximum demand is high, so that that decides only our generation capacity. What should be the be installed the generating station? What is the amount of generation be should install for a certain generating station? So this is peak demand decides the capacity of generation, and if this peak demand is high and if we are having low utilization, this means average demand is lesser. So this leads to low load power factor, and consecutively this will lesser this will increase the overall cost. If the load factor is very low as high peak demand, the capacity of electrical energy remains inactive for a long time, and this will increase the per unit cost of electrical energy to the customer. And improved load factor means to reduce the peak load demand, and this to reduce the peak demand, what are the things we can do? Like we have seen these various means to reduce the peak demand. Shift some load from on peak to off peak periods. For reducing this peak demand, we can do some load from on peak to off peak periods. There are some loads we can which is does not which are not type of critical loads which we can shift from on peak hours to off peak hours. Like we are having EV battery charging, one of the common example, one of the well-known example. We can do the charging of EV battery at the time of off peak hours, so that uh, we can uh, we can contribute in lowering the peak demand. This procedure is known as load shifting. And further, what is that? Reducing peak demand without shifting of load is known as peak saving or peak clipping. It will also reduce the total energy consumption. Means certain energy conservation uh, barely efficiencies loads we can apply, so that we are having better efficiency rate, so that it certainly demands lesser power. In that case, we can reduce the peak demand without shifting of load. So this is known as peak saving or peak clipping. And now if we see as we all know that there are commonly four types of load: domestic, commercial, industrial, agricultural. So if we see these four different types of loads on different factors that is load characteristics, like for demand factor, diversity factor, load factor. Here we are major focus on this load factor. Load factor is lesser for this domestic type of load. You can see 10 to 15% minimum. Load factor is minimum for domestic type of load. And for industrial type of load, it is maximum. We can usually visualize ourselves, because in industry, whatever the peak demand, most of the equipments that are installed there, most of them are running for approx most of the time. That's why load factor is increased. On the other hand, domestic type of load, it is on the weather, it is on the timing, that all loads are whatever the peak load, but we are having the peak load for domestic type of load. That does not necessitate that we are all loads are certainly running uh, for approx most of the time. So that is the that's why we are having minimum load factor for domestic type of load and maximum for industrial type of load, because in industry whatever the apparatus equipment installed, most of the time it is running throughout. Okay, all right. So we can write here the load factor is lowest for domestic type of load. While 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 load factor highest for industrial type of load. So this is the important characteristics of load factor. Now we will see some other factors. And one more important point I would like to mention, load curve. We know that load curve is the plot between the power demand to the time at different instances. And load duration curve means whatever the load demand, we are making the plot in descending orders. Highest power demand, we make it first and then continuously it decreasing at different time slots. So we can say that area under load curve, area under load curve is equal to area under load duration curve. And we can say it also, if we calculate this area, then it will give power into T, that is energy consumption. So it will give you amount of energy consumption. Now, if we see one of the important factors, one of the characteristics of load, that is diversity factor. Before that, no, we can. Okay, diversity factor. Diversity factor. Short form abbreviated it as DVF. So diversity factor is the ratio of individual sum of individual peak demand to the group peak demand. Writing it in short form abbreviated as, we can say that sum of individual peak demand is that I is equal to 1 to n pi max to the ratio of group peak demand aggregated. It is also called coincidence peak demand, aggregated peak demand. So PGR max. And second term is that coincidence factor. Remember one of the term, either diversity factor or coincidence factor. Coincidence factor is just reciprocal of diversity factor. So remember one term and just do reciprocal of other. Coincidence factor is the reciprocal of diversity factor. Coincidence factor is the reciprocal of diversity factor. Third important term is that demand factor. Demand factor. Demand factor, we write it as maximum demand. It is the ratio of maximum demand to the total connected load. It is the ratio of maximum demand to the total connected load. Diversity factor, maximum demand, we can say maximum of Pj divided by total connected load. Let us take it as TCL. So this is time demand factor. It is also one of the important characteristics for load. And further, if we see, we are having load diversity. Load diversity. This is comes in terms of watt, in terms of unit of watt. So it is the difference of sum of individual peak demand and group peak demand. Whatever the terms comes in the diversity factor, it is the difference of that only. So load diversity we can write sum of individual peak demand, sum of individual peak demand subtracts minus group peak demand. So load diversity is the power and is the difference of sum of individual peak demand Pi max minus P aggregated group peak demand or aggregated peak demand or coincidence peak demand. This is the load diversity. Now this peak demand, if we are having different columns for different types of loads, then how we can find the peak demand of the group? So peak demand of the group, peak demand of the group is determined as is determined as PGR max. Peak demand of the group is determined as C1 P1 max, individual peak demand for one section, and then C2 P2 max for second section, and then continuously it went for a number of whatever the number of different types of load or different types of section present for certain feeder or certain substation. So this is the peak demand of the group we can determine using this equation. Okay, and this the CI means C1, C2, it is called as contribution factor. Contribution factor, that is CI. And we can directly find if this contribution factor is not given in the question, it is not given in the problem, then how you can find this contribution factor through the table. For that, first you need to find out the time instant. There are two steps. First step is that you have to find out the time instant at which aggregated or peak demand is occurring. So first just see the aggregated peak demand and then find the time instant at which this peak demand is occurring, and then we will find the individual contribution factor for different classes, for different section, for different type of loads, for different type of sections present for this feeder or present for the substation. Class contribution factor, that it is the ratio of class demand at time of group peak demand to the class non-coincidence maximum demand. So this is the from this from this group peak demand we find the time instant. Now there is no work, there is nothing related with group peak demand. We are not using group peak demand for finding the class contribution factor. And at that times we will see that what is the class demand. So that will be numerator. You can see that will become numerator, and denominator will be the for that class what is the maximum demand, that is non-coincidence maximum demand for that peculiar class, for that specific class what is the maximum demand that comes in denominator. Okay, I hope you will understand this. Let me again just tell you that for finding the contribution factor we will first find this aggregated peak demand, and then for that aggregated peak demand we will see that time instant. And now we will just forget this peak demand. Now we are not going to use aggregated peak demand. What is the power? That is nothing related. We are just interested in the time instant. And for that time instant, we will see that for whatever the class we are going to find, we will see that what is the class demand at the time of group peak demand, means what is the class demand at that time. So that will come as numerator, and for that class what is the maximum demand, that will come in denominator. I have solved this type of problems in the tutorial session, so you will get from that help from that session also. And the last important factor is that loss factor. Loss factor LSF. It is the ratio of average power loss to the power loss at peak load demand. Power loss at it is the same as load factor, just the power loss terms comes with average or peak. Now we will see the demand side management. We know that demand side management includes all measures. We can write demand side management includes all measures, programs, equipment and activities and activities that are directed toward improving efficiency and cost effectiveness of energy usage on the customer side of the meter. So what is the term means demand side management? Demand side management includes all measures, programs, equipment, and activities that are direct toward improving efficiency and cost effectiveness of energy usage on the customer side of the meter. How we will achieve this? What we will get by doing demand side management? We are just reshaping the load curve, either daily load curve or weekly load curve, monthly load curve or yearly load curve. And this does not include outage or interruption. One of the important key factor in this demand side management is that we don't include outage or interruption in this part. We are just going to shape the load curve, whether it is daily load curve, weekly load curve, or annual load curve or monthly load curve. And the various types of means of demand side management we are usually apply are like this peak saving or peak clipping. In this, we reduce both peak demand and total energy consumption. And important examples are efficient control of air conditioners, heaters. So here, both peak demand and the total energy consumption gets reduces. And For valley filling, there is no change in peak demand, just increase in total energy consumption. When we are facing low power demand at that time, we are going to fill that valley. So for this case, we can say that valley filling, peak demand remains same, peak demand remains same, and total energy consumption will increased. Total energy consumption will increase. Examples are electric vehicle charging. We can do the EV battery charging at the time when there is power demand is lesser or during off-peak hours. And for load shifting, we are just remains the total energy consumption and reducing the peak demand. Whatever the demand occurring at the on peak hours, we are shifting it to off peak hours. So by that we are reducing the peak demand and total energy consumption remains as it is. Total energy consumption remains same. And deferrable loads means loads that allow time shift and interruption, like our washing machine, EV battery charging, that are called deferrable loads. And for this strategic conservation, that we will do by efficient lighting and air conditioning. In this case, we reduce both peak demand and total energy consumption. We are having to just shift load curve downwards in this strategic conservation. It will also gets reduced and it will also gets reduced. We shifts the load curve downwards. And for this, just as planning a strategic load growth, planning of distribution system, we are going to build the new loads, means efficient planning of power distribution system. In this case, peak demand will also increase and sorry, total energy consumption and total energy consumption both will increase. And in this case, shift load curve upwards. So this is for module 1, load characteristics and load management. And some of the important things are different tariff structures imposed by the utilities, and these are flat demand rate structure, a constant price per kilowatt hour in this, and the slope is just remains as it is, and this block meter rate structure lower prices for greater outages, greater usage means slope between the energy rate and this time energy rate and time, it will vary upon greater usage. And demand data structure separate charges for demand and energy means there is separate charge for kilowatt, and for energy there are separate charge for kilowatt hour. Seasonal data structure means higher prices per kilowatt hour used during the season when system peak demand occurs. And this time of day or of peak load pricing structure means higher prices per kilowatt hour during used during the peak period of the day and lower prices during off peak period of the day. This one is very important. Block meter data structure and flat demand rate structure usually implies. In this block meter rate structure, what happens? The prices get reduces upon increasing the upon a, if we are increase the usage of power. Initially, for certain amount of kilowatt energy, it is it is having different prices, and then after that it will prices will gets lower down. Now we will see the power distribution networks. I brief overview. If we see our structures, the hierarchical structure of power distribution networks, we are having generating station, and from the generating station we are having transmission lines to the load centers, and transmission lines is also composed of two different sections, the main transmission line and sub transmission line. And further we are having distribution network, and distribution network is usually of two types: primary distribution networks and secondary distribution network. Primary distribution networks connected between the distribution substation to the utility transformer, and then secondary transformer connected between the secondary distribution network connected between the transformer to the load center. So if we write the hierarchy of power distribution network, we can say that hierarchy of power delivery system. So first we are having generating stations, generating stations, and then transmission network comes, transmission systems, and then we are with substation. We called it as transmission substation that lowers down the voltage level. Transmission substation, and this will connected to the sub transmission system, sub transmission systems, and then this is called as distribution substation, distribution substations, and this will connected to primary distribution systems, primary distribution systems, and this is primary distribution system comes to the distribution transformer. Distribution transformer, and further we are having secondary distribution systems, secondary distribution systems, and this is connected to end user customer or customers, end users or customers. And we write down this voltage level of transmission systems. Usually it is between 69 kV to 1100 kV, and this sub transmission system 34.5 kV to 230 kV. And further this voltage drop down for primary distribution system 2.2 kV, 2.2 kV to 34.5 kV. And this one is for in USA type countries it is 120 to 118 to 120 volt, and this is for India 220 to 230 volt phase. This is Indian utility voltage level, Indian utility utilization voltage level, utilization phase voltage level. For line to line it is 400 volt. And for this generally we are having 11 kV or 33 kV. In India we are having 11 kV or 33 kV in Indian distribution system for primary distribution system. So we can see that distribution networks are of two types: primary distribution network, that in India if we see the voltage level that is 11 kV and 33 kV, and for secondary distribution networks that connects the distribution transformer to the end user customers, and this secondary distribution networks voltage level is uh, 220 to 220 to 230 volt phase voltage. So now if we see the difference between transmission and distribution networks, then transmission networks are of mesh types. Transmission networks are mesh types. It is having different power flow available, and distributed networks are of radial type. Load is relatively balanced in transmission network while it is unbalanced in distribution network, and lines are transposed in nature in transmission network and non-transport in distribution network. Power losses is sure lower due to lower voltage level, and this power losses in higher is, is high in distribution network due to lower voltage level. On the other hand, transmission network power losses is lower due to higher voltage level. Fault occurrence is less, and this distribution network is prone to fault occurrence. And one point I would like to add here, in radial distribution network, in radial distribution systems, number of nodes is equal to number of lines plus 1. Number of nodes will be always greater than number of lines because it requires two nodes to form a single line. So the number of nodes is equal to number of lines plus 1. Now we will see the different types of busbar arrangements or switchgear arrangements. This is also called as switchgear arrangements. So different types: single bus scheme, single bus with a sectionalizer scheme, single bus with a sectionalizer and two power transformer scheme, and main and transformer bus scheme, double bus bar scheme, ring bus scheme, break and half scheme that is most commonly used. Break and half scheme. So in single bus scheme, we can see that whenever fault in bus bar would happen, it take the whole station out of service. So this is the cheaper, but it has a disadvantage of fault occurrence, that it has disadvantage if any fault occurs, then it leads to whole substation out of service. So reliability is lesser, and on the other hand, it is cheaper in cost and easy to implement. And this single bus with transfer bus scheme, we can say that here main bus is there and with transfer bus. Main bus is always energized, and this bus tie breaker is normally open. It is normally open, and whenever we require to just do the maintenance circuit breaker, we close this tie breaker and transfer the power through the transfer bus to the customers while repairing the circuit breakers. So at the time of maintenance, transformer bus gets energized while the mains bus will be out of service. Next, we are having double bus bar scheme. Double bus bar schemes, it is having two buses, both are it both are always energized and connected by a tie breaker. It provides operational flexibility, that is possibility to move loads between buses. And in this double breaker scheme, one feeder is connected by two circuit breakers with respectively buses. So these are having operational flexibility, possibility to move loads between the buses. Either we can take power from the w- from the one bus or the second bus. So we can see that here these are circuit breakers. These are circuit breakers, and these are isolators. So one important point is that circuit breaker operates at no load condition, operates at on load condition, while isolator operates at offload condition. Now, if we see the difference between sectionalizing switch and tie line switch, we can see that there are different feeders F1, F2, F3, and sectionalizing switch we can see that in a particular feeder these are used to connect the different section of that feeder, while this tie switch used to having connection point between different feeders, and this tie switch remains open. Normally it is open in condition, and while sectionalizing switch it is closed. If there is fault happens, this sectionalizing switch gets open so that this faulty part gets removed removed from that feeder and the power supply remains continuous. While this tie switch be used in the emergency condition if we take the power if we want to take the power from the other feeders. Sectionalizing switches normally it is closed. It is used in fault condition. It is used in fault condition. During fault condition it is opened. It is opened during fault condition. While this tie line switches normally it is open. It is open, and this used in emergency condition or maintenance condition. During that condition it will be closed. It is closed during emergency condition. So that is more important point with sectionalizing switches and tie line switches. So don't get confused with the terms. Now we will see this voltage drop and power loss computation for typical distribution feeder in power distribution system. For that we are defining this K constant term. First, we are looking into voltage drop and power loss, computation for typical radial distribution feeders. Here we define the K constant. So K is a constant that can be defined as percentage voltage drop per kilovolt per kilovolt ampere kilometer. And if we derive this term, then it comes as r cos theta plus x sin theta into 1 by 3 into 1000 VR V base. It is written in per unit form. If we write in the actual form, then the S3 phase comes into numerator. So it's unit will be voltage drop per unit kVA kilometer, or some may use mile. Now if we write this power loss, total power loss and voltage drop, voltage drop of radial feeder for uniformly distributed load, that with rectangular service area, with rectangular service area. So here, so the term will come, voltage drop will be half of IS ZL. So L effective will be, if we want to just use the lump load, then we can say that X is equal to L by 2. The voltage drop will be similar for a lump load if the lump load connected at the midpoint of the feeder, and this total power loss is 1 by third IS square RL. So here for lump load, where should be connected? It is should connected at the 1/3 length of the feeder, L divided by 3. And similarly for uniform distribution with triangular service area, so TPL and and VD of radial feeder of radial feeder for informally distributed load with triangular service area it will be voltage drop will be 2/3 of IS ZL. So for lump load where it should be connected X is equal to 2L for getting the similar voltage drop X is equal to 2L divided by 3 and total power loss will be 8 divided by 15 IS square RL. So X is equal to 8L divided by 15. With triangular surface area means it means that we are having increasing load density. Now we'll see the general case for substation service area within primary feeders. General case substation service area within primary feeders. And we take n is equal to n is less than n greater than or equal to 3. So if we say that area served by one of the n feeders will be area served by one of n feeders. N feeders is n is equal to ln square tan theta ln is ln is linear dimension of the primary feeder service area. Linear dimension of the primary feeder service area. Ln is the linear dimension of the primary distribution service area. And theta will be 360 degree divided by 2n, where n is the uh, number of primary feeders. N is number of primary feeders. Okay, and this next term will be kVA load served by one of n feeders will be kVA load served by one of n feeders is it is we are looking terms for uh, uh, a square service area, hexagonal service area, hexagonal substance service area. So KVA load served by one of n feeders will be Sn is equal to D into An. An is, we can see from the previous term, and we are having percentage voltage drop of the main feeder will be percentage voltage drop KLESN. So we can see that lump load we can connected at a point on the main feeder at a distance of 2 by third of ln from the feeder point. So LE is will be 2 by third of ln. Therefore, we can write percentage voltage drop K into 2 by third of ln Sn, and then Sn we can write DAN. Percentage voltage drop will be K into 2 by third ln DAN, and further An we can write in terms of tan theta. So we can having the final expression as K into 2 by third of D ln cube tan 360 degree divided by 2n. So this is the expression. Sit. Just wait for 1 or 2 minutes. I think some problem in my computer.
And hello.
Yes, yes,
Can you just explain the last module? Actually, make doubts in that in last module.
yes. Tell me.
And the smart grid in the smart grid module,
Where? Which slide number?
sir. The last module, sir. The smart grid concept.
Okay, Miss last module, Mr. Big 12, right?
Yes, sir.
So what is in that?
Sir, the automatic. My question is the where is the DGs or DERs are connected in the grid? Means the if I am a distributed energy source, then where the how the I can go through the power lines to distribute my over power or some surplus power.
So we will see, we are having this optimal power location. We will see that how, what is our objectives, means total power loss. We are we are placing the distributed generation so that if we are having a duty that we can reduce the total power loss, or we can also increase the reliability of the network. It is that, means it
Sir,
depends. We have, it depends on our objectives.
okay, sir. Mm.
I think you are not able to get it.
My question is the where is the distributed energy resources are surplus their power to the grid, means the 33 on the 33 kb, on the 66 kb, on the 132 kb, on which on which voltage sides they can provide their surplus power. My question is that.
Okay, so if this means there are many ambiguity like that, means distributed generation according to if you see according to Ackerman, then according to him, purpose and location defines the distributed generation, and the location should always at the distribution at the in the distribution system, not in the transmission system. So for distribution system, either you placed at the primary distribution system or secondary distribution system, and the primary distribution system is having voltage level of 11 kV or 33 kV, and for the secondary
Okay, sir.
system that utilization voltage level. But
Okay, sir.
in literatures you may find that uh, it means if according to IEEE that it is defined as the distribution generation capacity should not be greater than 10 MVA. But there are some literatures you may find that one microgrid having more power capacity or like that.
Okay, sir. And another question, means the 33 or 11, directly I connected the distribution cable on that bay, or the on direct or the 11 bus can connect directly on that bus or separately on that bus.
Means whatever
Means the mean means
if your if your like if you are having solar PV panel, then you
Yes,
are
sir.
having inverter. So
Yes, sir.
if you are having inverter, then suppose if you are not for using the voltage level of like 2 level or 3 level, then for you are not get that more voltage level for directly connect to transmission system.
No, sir. My question is not that. My question is it is the conventional electrical system where is the 11 kV bus is present, and in my home another DG or DER or solar panel or windmill system, anything. Uh, can I directly one cable is connected to the direct on 11 kV bus or somewhere else? I'm a little confused about that. For extra surplus power distribution.
uh, okay, means you want to ask that, means we can directly connect to transmission system or we having some what transformer required.
Yes, sir. Yes, sir. Exactly.
Yes, means whatever the you're generating the power at home or means at a smaller level, it will be of a lower voltage level. Then it definitely require this transformer. If you but for lesser power system, we cannot connect to the bigger voltage level. We could directly feed to the distribution system. It is generally
It
having
can, it can,
smaller voltage.
it can also available. It can be provided from the actual conventional method, or by adding some new distribution system. It can be happened.
Oh, okay. For a for having you are saying that you are having different type of distribution. No, no, it is not like that. Means
uh,
whatever the existing distribution systems, you
yes, sir.
you can feed to that only.
And
Not
my
we
actual
cannot
actual my
change the
basic
yes.
Actual, my basic question is my conventional source and my DG or DER source meeting at the same 11 kb point or same 400 point or same 220 point. Where is the common point where two sources are meet? My question is that.
It depends upon the power level power of your DG capacity also, and also
Okay, sir. But there is no harmful for the DG or DER when I connected both source in a single point.
it means you are saying DG or distribution system, right?
Yes, sir. Yes, sir.
Yes, for DG you are directly feeding to the distribution system. That means you are having power electronic converters, and that power electronic converter means somehow you are providing harmonies to the system. So
Yes, sir. But my question is that where is the but, what is the conclusion when two sources meeting in a 11 bay or 11 bus or 200 440 net 440 distribution channel? What is the consequences?
consequences is that like that means if you are not having a proper voltage level, then it may having reverse power flow also. Something means I'm not getting your question properly, so it's better you can write mail to me, because in written we can, I am putting down my mail, so you write mail to me because it is a research type of question.
Okay, sir.
I have just written down in my mail in chat box, so you can mail to me. Okay, Amit.
Yes, sir. Yes, sir. Thank you, sir.
Hmm.
Sir.
Because if we discuss this, might our time will also get killed. This.
Yes, sir. Yes, sir. Please, sir.
Okay, all
Thank
right.
you. Thank you, sir. Thank you, sir.
Welcome. So we are here and just writing down the conclusion for a square substance service area and this hexagonal substance service area. In theta, tan theta, and then we are having percentage voltage drop in. In is 4, then if number of primary feeders is 4, then theta will come out 45 degree, and tan 45 is 1.0, then k2 divided by 3 d L4Q. So 6 is theta will be 30 degree, then tan theta will become 1 divided by root 3. So percentage voltage drop will be k to 2 divided by 3 root 3 dl6q. And now the last term is the total kVA supplied from the substation. Total kVA supplied from a substation TSN is equal to NSN TSN N into DAN. So this is for the second module, power distribution networks, and Next, we will see that reliability assessment of distribution network. So there are different types of reliability indices, like indices for sustained interruption, indices for momentary interruptions, and load and energy based interruption. So here we are going to see most of the indices that are either sustained interruptions or load energy based indices. And the conventional these terms are denoted as total number of customers served as NT, total number of customer interruption as sigma NI, total number of customer interrupted as CN. And in this CN, the customer is counted once regardless of the number of times in interruption. So the CN denotes the customer only once. So here the customer is counted once regardless of the number of times interrupted. Regardless of the number of times interrupted. Regardless of the number of times interrupted. So SIFI means system average interruption frequency index. System average interruption frequency index, that is sigma ni divided by nt. And for SIDI system average interruption duration index. SIDI means system average, just numerator gets changed. In this sigma ni, in the place of sigma ni it will come sigma ri ni. So for SIDI system average interruption duration index. Average interruption duration index. And next term will be CAIFI, customer average interruption frequency index. Customer average interruption frequency index. And CAIDI means customer average interruption duration index. Just remember all this term, it will be helpful in your final exam. Duration index. ENS means energy not supplied. Energy not supplied. And RI, just in the previous term, RI is what? RI is RI restoration time for each interruption event. Restoration time for each interruption event. ANS, that means average energy not supplied. L average I is average load connected at load point I, and this average customer curtailment index is the ratio of NS to the CN. Average customer curtailment index, and ASI is average service availability index. Average service availability index. And here I have denoted it for the yearly basis, so number of hours per year. So 88, for different duration it will vary, ASI is different. So here I have used for yearly basis. So number of hours in a year, if you are calculating for week then it will be different, or for month, for a day, number of hours per year. Now ASIDI, average system interruption duration index. Average system interruption duration index, and CTAID is customer total average interruption duration index. CTI is hybrid of KAIDI and is calculated the same except the number of. So KAIDI we have seen that what it is that KAIDI BC RINI divided by CN, N RINI divided by sigma NI. Yes. So in the place of sigma Ni, it will Cn. The number customer is counted only once, regardless of the number of interruption. Okay. Now we are having different reliability terms like be defined mean time to failure. It is m bar. So it is 1 divided by lambda. Lambda is mean failure rate, and then mean mean time to repair, MTTR. It is denoted as R bar 1 divided by mu. So mu is mean repair rate, and mean time between failure MTBF will be T bar is equal to M bar plus R bar. And if we derive want to write for the repairable components in series, then we can say that reliability of repairable components in series. So mean time to failure means our operation time or our uptime. It will be M bar series 1 divided by sigma lambda I, or mean time to repair, is equal to R bar series is equal to sigma lambda I Ri bar divided by sigma lambda I. And further, if we write the reliability terms for reliability of repairable components in parallel, then mean time to failure M bar parallel will be is equal to 1 plus sigma lambda I Ri bar plus divided by product of lambda I summation of Ri bar, and this R bar parallel will be Ri sigma Ri. And if availability and unavailability, we can write of components. Availability denoted as A and unavailability denoted as U. So unavailability is mean time to repair to mean time between failure. So R bar divided by R bar plus M bar lambda divided by lambda plus U. A is equal to A minus U. So it will be M bar R bar plus M bar is equal to mu lambda plus mu. So this is for reliability assessment of power distribution network. Next we will see various power quality issues in distribution networks. So power quality problems can be of transient, short duration voltage variation, long duration voltage deviation, voltage imbalance, waveform distortion, voltage flicker. If we see short duration, so we are having power quality issues like transients, short duration, voltage variation, long duration voltage variation, long duration voltage variation, voltage imbalance, voltage imbalance. These are commonly the categorization of power quality issues, voltage imbalance, waveform distortion, waveform distortion, voltage flicker, etc. So if we see our short-term voltage duration, short-term voltage variation, short-term voltage variation, then it is mainly categorized classified as voltage sag, voltage swell or interruption. Voltage sag, voltage swell or interruption. It exists for a few cycles to a 1 minute, so its time duration is less. While on the other hand, if we look into long term voltage variation, then it consists of over voltage. It sustains for more than 1 minute. Long term voltage variation sustains for more than 1 minute, while the short term voltage variation sustains for few cycles to a 1 minute. Under voltage, over voltage, under voltage, and this sustain interruptions. Now we look into the how to remove these power quality problems in the distribution systems. The, we use this custom power devices. So therefore we can write custom power devices used for power quality improvement, used for power quality improvement, and they basically consist of reconfiguration type or compensation type, reconfiguration type or compensation type, compensation type. Reconfiguration type examples are solid state current limiter, solid state current limiter SSCL, solid state breaker before breaker, solid state breaker, and solid state transfer switch, solid state transfer switch. So these reconfiguration types are network configuration devices that are usually called switchgear also, that is usually switchgear, and they include current limiting, current breaking, and current transferring devices. While on the compensation type, we are having D statcom, distribution statcom, and then we are having DVR, then we are having UPQC. It is combination of D statcom plus DVR, and it is shunt device. It is connected in shunt, while DVR is a series device. It is connected in series. This is used for either compensate load, correct its power factor, and improve the quality of supplied voltage. This DS.com usually as shunt power devices, and we are improving the current, and where this series devices we are improving the voltage profile. Means for from DS.com we are improving the power factor, we are improving the supply quality of supply voltage. On the other hand, DVR on we are using it for we are using for maintaining this voltage profile. And if we see that is combination of both DS.com and DVR. Now we will see the load flow analysis of radial distribution network. So we have used the forward backward load flow analysis. Forward backward sweep load flow approach for radial distribution network. And we know that advantage of radial distribution that power flow is unidirectional. So we can determine both voltage profile and power loss of a network. And let us what we first apply in this forward backward shift load flow. First we apply this backward shift. In backward shift we determine the branch current. To determine the branch current, to determine the branch current, and it is application of KCL. It is application of KCL. We find this ILI load current, and then we find this branch current. Load current, how we can find load current, this PI minus JQI VI conjugate, and it always starts from the computation, starts from the in nodes or terminal nodes, and this needs more computation. We first need to find this load current, and then we find this branch current also. Then we apply the forward shift. Then we apply the forward shift to determine the bus voltage. The aim of our load flow is that to determine the voltage profile and the power loss of the network. So at last we apply the forward shift, and after applying this backward shift to determine, here we will determine the bus voltage. It is application of KVL, and here this computation start from the slack node. Computation starts from the slack node. So what we do, suppose we are having buses, 6 buses, and just connected in one line. So V2 bar is equal to V1 bar I12 R12 per unit plus JX12 per unit. I12 we find from the backward shift. V1 is already known, that is slack node. We take it as 1 angle 0, and consecutively we can find V6 like V5 minus I5 R56 per unit plus JX56 per unit. So firstly, line currents are updated in backward shift and then node voltage are updated in backward shift. That is the important point. Now we will see this module 5, reactive power compensation distribution system with shunt capacitors. So this is important question, many of having doubts, which of the following consume leading reactive power? And this multiple select question. So for transformer, we know that we take it as we assume it as inductor. So this will this will not consume leading reactive power. It will consume lagging reactive power. While overexcited synchronous generator and this transmission line loading greater than surge impedance loading and capacitors we are having look into it. So if we want to make V curve for synchronous generator, then it looks like this. Sorry. So all overexcited, either it is motor or generator, all will consume leading reactive power, and that will help, that will provide, that will improve the power factor, and that will provides the lagging reactive power, delivers the lagging reactive power. So this one is also correct, and this transmission line with loading greater than surge percent is not correct, because transmission with loading surge, if we having more than surge impedance loading, that means we want some capacitors to restore the voltage, shunt capacitor to restore the voltage. So this is not correct, and the last one is capacitor. It is correct option. So I just want to tell you that means if Q is positive, then always it is lagging reactive power. And if Q is negative, means it is leading reactive power. Now, if we see in terms of generator or motor, like in one terms we can write generator, and other side we can write motor. So for generator, if Q greater than 0, then it means that what is the basic feature of generator? It all provides, means delivers lagging reactive power, delivers lagging reactive power. And if Q less than 0 delivers leading reactive power. And just opposite that, if delivers means that consumes leading reactive power. Consumes leading reactive power. Motor, for motor Q less than 0. For synchronous generator means Q greater than 0, that is overexcitation case. Q greater than 0 means we tell for it is load type, so it we write in terms of consumption. So consumes lagging reactive power. And Q less than 0 means consumes leading reactive power. Motor you can say also it as load. So consumes leading reactive power means supplies or delivers lagging reactive power. Okay, so that's why reactive power capacitor comes as negative and it delivers lagging reactive power and thus it improves power factor. So next we will see the capacitor placement thing. So for that first we will see lambda, one of the important terms. Lambda is equal to I2 divided by I1. I2 is reactive current at the end of line segment. Reactive current at the end of line segment to the reactive current at the beginning of line segment. Reactive current at the beginning of reactive current at the beginning of line segment. So lambda is equal to 1 means lumped loads or concentrated loads. Lambda is equal to 0 means uniformly distributed load. And alpha is equal to 1 divided by 1 plus lambda square. And second term is C is equal to IC divided by I1 kVA of capacitor installed. kVA of capacitor installed. Total reactive load. If we want to write the analytical method, so we can write another phase. If we want to write this analytical method for single capacitor bank placement. Then we are having power loss reduction. Delta PLS will be 3 alpha 1 minus lambda C minus C square plus CQ divided by 4, differentiating with respect to C and equating to 0 will give the optimal value of C. Optimal value of C will be 2/3 and x1 is equal to 2 by 3 1 divided by 1 minus lambda. This is very important term. Very important term, these two. Now if we put all this, then delta PLS will become 3 8/9 alpha 1 minus lambda, and for lambda is equal to 0, then delta PLS is equal to 8/9 per unit. For the capacitor placed at x1 is equal to 2 divided by 3 per unit, with C is equal to 2 by 3 per unit of size. So this is well known used 2 by third rule. Thumb rule for capacitor placement. Okay, now this for economic aspects you can, these terms are very important: present worth factor or discount rate. So present worth factor, and it is related to discount rate as 1 divided by 1 plus d power t, where t is number of figures and the value today of x rupees can be uh, what the value of future is described by this equation, and levelized value of q over t years will be q into d into 1 power plus d power t divided by 1 plus d power t minus 1. And this difference planning consists of two parts: a static planning and dynamic planning. Dynamic planning where load growth is considered, and where the load growth is in network or addition of new nodes is happening, that we should consider. And this there are various optimization objectives and constants for formulation of objective functions. And these objectives can be of minimizing total installation cost of new substation branches. This you all please look into it. And the solution approaches for multi-objective optimization is given as, and this classification of solution strategy you can find out. And this the important definition of distribution is also one of the important part which I have taken from this book, which I have taken from this reference Ackerman. So that's all for today's session. If you're having doubt, you can ask. This is the last session. This is the revision session. All the best for exam, and hope you all do great in the exam, and you all secure elite certificate, and some of you may get elite plus gold certificate in this NPTEL certification course. Thank you all for be having with me during this entire session. And if you are having a doubt, and then you can ask further on this email ID that I have shared in chat box. Thank you.